Okay, we're on section 3.1, example 2. So this one asks us to find the limit as x approaches 3 of this particular piecewise function. And I had this all up, but the program crashed on me, so I just decided to leave it up. So this is called a piecewise function, and if you're not clear on how piecewise functions work, I can post up a video for Khan Academy about this. Basically, you define the function differently depending on where you are in the domain. So in this particular piecewise function, for all values of x except 3, if x is not 3, the function is defined like this. At x equals 3, the function is defined differently. It's defined to be 4. So what we're trying to do here is find the limit as we approach 3. We can do this with a table of values. But really, right away, we can notice that, remember, with limits, what matters is what's happening near the number, this number here, 3, not what happens right at the number 3. So we only care about, since we only care about what's happening near 3, how is the function defined near 3 but not at 3? It's defined to be like this. So this is really the limit that we're interested in finding. You notice I've already got a 2 there. See why that is the case. So the table of values, we're going to put all these numbers, just like we had done on the previous example, that are near 3. These ones here. I put 3 there, but I put an x there. Even though it is defined, I don't care how it's defined, so I just put an x there. So we plugged in all these values into the function, into 2x minus 4, because that's how the function is defined if x is not 3. None of these numbers are 3, so they must be plugged into here. So when I plug them in, these are the values that I get. And what you can notice is that the closer that we get to x equals 3, the closer that these values, the y values, seem to be getting to what number? It looks like 2. So that is why we conclude that this limit is actually 2. Notice as well that if I took that number 3 and just plugged it right in there, I would get 6 minus 4 is equal to 2. Not a coincidence. And graphically, we can sort of see, again, why this is or what's happening on this particular function. So when I graph it, and this is a good practice for actually graphing a piecewise function just in general, I'll put in these values that we are focusing in on, the numbers near 3. Again, the function is defined to be this linear function for pretty much all values of x. I'll put in a few x values, a few y values. Okay, and since it's linear, really all I need is 2 points. So I'll pick, let's suppose we pick the number 2. If I plug in 2, I get 0. So the output is 0 at 2. If I plug in 4, the output I get is 4. So it's basically going to go through these 2 points here. Now at 3, we know that it's not defined to be 2, so I'm going to put a hole there. And this is kind of what the function is going to look like. Okay, the hole is there because, again, it's not defined to be 2 at 3. How is it defined to be at 3? It's defined to be 4. So the way that we can denote that on the graph is like this. Put a dot up there at 4. Okay, now graphically speaking, the way that we can see that this limit is what it is, we plugged in the numbers near 2. So I'm going to say 2.5 and 3.5. That's this value. When I plug that value in, we saw that the output was 1. For 3.5, we saw that the output value was 3, and we can see that graphically as well. You can see that the output there is 3. Okay, so what we've actually done is we've sort of created a window around the number 3. And then when we plug those endpoints of that window in, we see that it creates another window over here. If I plug in numbers that are closer to 3, like say these two, and we did that on the table, maybe that's like 2.9 and 3.1, their output values, you can notice here, what do? Well, they seem to get closer to the number 2. The closer that I got to 3 here resulted in a smaller window around the number 2. And you can see that if I get even closer, what's going to happen to this window over here? It's going to get even closer to the number 2. Based on the table and this graph, we must conclude then that this limit is actually 2. Again, notice that doesn't, the fact that it's defined to be 4 here has no bearing at all on what the limit actually is. Okay?